Throughout your networking career, you're likely to see many topologies, many different networks with lots of different components, but what we see on screen is just a basic sample of some of the components that you're likely to see a lot. For example, routers and switches and clients and file servers. We've got links out to a remote network such as the internet. Let's spend just a few moments and zoom in on some of these different elements that we're likely to find in a network. For example, the end user is using some sort of a client. Maybe it's a desktop, maybe it's a laptop, maybe it's a smartphone or a tablet. But a client device is how the user interfaces with the network. And one resource that they might be trying to access on the network is a file server. A file server can be thought of as a computer that shares its hard drive with clients. And of course, depending on the network operating system running on the file server, there are different ways of setting up who has permission to access which files. But for the purpose of our discussion, let's just think about the job of a file server. The file server is going to make files available to our clients. And because all the clients are pointing to this same shared repository, one client can make an update, and that update is suddenly reflected when the next client downloads the file which was updated. But how do the file servers connect into the network? Well, typically, they're going to be connecting into the network by connecting to a switch. And a switch is referred to as a layer 2 device. We'll be talking about that later. A switch, specifically an Ethernet switch, can make forwarding decisions based on what it learns from the attached devices. You see, inside the file server, inside the client, there is a network interface card, an NIC or a NIC. Inside the Ethernet attached device, there is an address that is burned in physically to that card. It's called a MAC address, MAC. That's a media access control address. And the switch can learn which MAC addresses live off of which ports. And once it learns that information, it's going to see a frame destined for a particular destination, and it's going to say, well, I learned that that MAC address lives off of this port, so I'm going to forward that frame out of that port. And you also see on screen a router. A router is a layer 3 device, meaning that instead of making forwarding decisions based on things like MAC addresses, physical addresses, a router, it's going to make forwarding decisions based on logical addresses, networking addresses. We're going to have a big discussion later on about networking addresses and how they work. But for now, just understand that architecturally, as we think about a network, the end user is connecting into something like a switch, and switches can connect to other switches, switches can connect to routers. But as our network starts to scale, and we have different network addressing concerns, as we'll get into later, a router can give us that scalability. A router can also give us flexibility and allow us to connect to non-Ethernet devices, such as connecting out to the internet. And you also notice in the diagram that we have different media interconnecting our devices. We might have category 6 twisted pair cabling connecting our end user devices and our file servers into a switch. Maybe we have the same thing between a switch and a router. We could use fiber optics in some cases. We've got different wide area network links coming in from our service provider to get us out to the internet or some other remote network. And that's another topic that we'll be covering. What types of media are used to get us around the network? And now that we've had this brief introduction to some of the fundamental components in the network, we need to start thinking about how to classify networks. We can classify networks based on how geographically dispersed they are, or how they're interconnected. For example, on screen, this is a network that we're assuming is in a single building. Within the building, this network that we see is a LAN, an LAN, a local area network. But you see, there's a WAN, a WAN, a wide area network link that's connecting us off somewhere else. If you're working on an older network that's been around for a while, you might come upon some legacy network components. Let's take a few moments and make sure you understand the function of some of these components. For example, we've got a hub, which would be used in older Ethernet networks. We've got a MAU, an MAU, a media access unit, that you might find in older token ring networks. And we also have a bridge, which is the predecessor to the modern day Ethernet switch. Let's check them out. Let's consider an Ethernet hub. A hub is an early Ethernet device, a legacy device, that used to be used quite a bit to interconnect things like clients and servers, any kind of device that wanted to get on the network. And one of the important characteristics to know about a hub is that it doesn't really make forwarding decisions. It's not analyzing any sort of MAC address or IP address. It's not analyzing anything in order to make forwarding decisions. In fact, sometimes it's simply referred to somewhat crudely as a bit spitter. It takes bits in on one of its ports and just repeats them out of the other ports. For example, on screen, if a PC sends a packet into the hub is going to regenerate that packet out all of its other ports, so everybody connected to the hub sees that traffic. And like we said, this was used in early Ethernet networks, and the competition back at this time was Token Ring. That was the other predominant technology in local area networks. Also, something to understand about a hub is that we're dealing with a single collision domain. All of the ports on this device belong to one collision domain. Let's remind ourselves what a collision domain is all about. If a PC wants to transmit on this shared Ethernet network, what it's going to do is use an approach called CSMACD. Carrier Sense Multiple Access with Collision Detection. It's going to listen to the network to see if anybody's talking at the moment, because we can only have one packet at a time on this shared Ethernet segment, and if it concludes that the coast is clear, it can transmit. But let's say that the PC and the laptop, they're simultaneously listening to see if the coast is clear, and they hear the same period of silence. What's going to happen? Well, they might transmit at about the same time, resulting in their two packets colliding. That's known as a collision. The packets are corrupted, they have to be retransmitted, but remember what CSMA CD stands for? The CD stands for collision detection. The devices can detect that a collision occurred and they can retransmit. And while this may not be a major issue when we only have maybe 3 devices connected to a hub, can you see how this is simply not going to scale very well? It's not going to scale to larger networks because we only have a single collision domain. We can only have, in other words, one packet on the network at once. That's not going to scale to hundreds or thousands of devices. Also, we have a single broadcast domain. A broadcast packet is a packet that is sent out to all of the workstations, all of the Ethernet devices on a subnet. And the hub is going to take a broadcast in on one port and repeat it out all of the other ports. It's not separating broadcast domains, it's not separating collision domains. In fact, all of the ports belong to the same broadcast domain and to the same collision domain. The next of our legacy devices that we want to consider is a MAU, a Media Access Unit. A media access unit, much like a hub, could be used to interconnect clients and servers and other network devices, but instead of being used on an Ethernet network, it was used on a token ring network. Similar to a hub, a MAU does not make forwarding decisions, it simply does token passing. A token that arrives on one interface is going to be sent out of the next interface, and it's going to return and it's going to be sent out of the next interface, and so on and so on. Logically, even though it looks like a star topology, logically what's happening inside of the MAU is that it is a logical ring topology. There is a token that is circulating around all of the devices connected into the MAU, and as a result, this was used in early token ring networks. When we discussed a hub, we talked about the concept of a collision and the fact that we had a single collision domain. With token ring, with token passing, a device's access to the media is more deterministic. When it's your turn, when you receive the token, it's your turn to transmit on the network. As a result, there's not the issue of collisions that we had with a hub, so there's no collision domain to consider. That doesn't apply here. There is, however, a single broadcast domain. If a broadcast is sent by one of these devices, it's going to be seen by the other devices. There's nothing blocking the broadcast. Let's consider an Ethernet bridge. A bridge is going to separate a network into different collision domains. If a bridge has 2 ports, as early bridges did, that would give us 2 collision domains, as pictured here. We might have a hub connected into each of the bridge ports, and the hubs themselves, they're in their own collision domain, meaning that if a collision occurred because a laptop and a PC on one hub sent packets at the same time and they collided, that would impact everybody off of that bridge port, but it would not impact devices connected to the other bridge port. And unlike a MAU, unlike a hub, a bridge does intelligently make forwarding decisions. It's going to learn, as it sees frames flowing through the network, it's going to learn the MAC address, the media access control address, the 48-bit address that's burned into these network devices. It's going to know that the laptop with this 48-bit MAC address resides off of port number 1. And this file server with this other MAC address, it resides off of port number 2. Then, later on, after it populates this MAC address table, if it receives a frame that's destined for a specific destination MAC address, it's going to consult its MAC address table and realize, oh yeah, this MAC address, I learned it earlier. That's a MAC address that lives off of port number 1, and it's going to forward that frame out of port number 1. And a bridge is really the predecessor of the modern day Ethernet switch. Because like a bridge, an Ethernet switch is going to separate our network into different collision domains. Each port on an Ethernet switch is in its own collision domain, just like a bridge. An Ethernet switch is going to make forwarding decisions based on MAC address information, like a bridge. One of the big differences, though, is performance. Back in the mid-80s and early 90s, when bridges were more popular, a bridge made its forwarding decisions in software, while an Ethernet switch has special circuitry called an ASIC, an application-specific integrated circuit that's going to allow the switch to make forwarding decisions in nearly real time. So it's significantly better performance-wise than a bridge. We also tend to have much higher port densities in an Ethernet switch as opposed to a traditional bridge. But getting back to the discussion of a bridge, this bridge has 2 ports, therefore this specific bridge has 2 collision domains. But what about broadcasts? Can a broadcast traverse a bridge? Yes, it can. In fact, we need a router. A router is going to separate broadcast domains. A bridge does not. That means that a broadcast sent from a PC off of one of our bridge ports, it's going to be seen by all of the other devices off of that same bridge port, in addition to all of the devices connected to the other bridge port. We're not blocking broadcasts with a bridge.